In this video, I'm going to introduce you to some of our basic rules of differentiation, and these are the shortcuts that we've been talking about that allow us to bypass the application of the limit definition of the derivative and find our derivatives much quicker and easier. The most basic of these rules is the constant rule, and this is the differentiation rule that's applied to a constant function like y equals 2. So for y equals 2, let's just think about this graph for a moment. If I sketch a graph of y equals 2, it's just a horizontal line crossing the y-axis at 2. And remember, whenever we're finding the derivative of a function, what we're really finding is the slope. And for this constant function, and for any constant function, the slope is going to be 0 because it is a horizontal line. And so that means that the derivative of y equals 2 is equal to 0. And this is going to hold true for any constant function. And so we can say in general that the derivative of a constant, of any constant, is equal to 0. And that's our first basic derivative rule. We will be adding that to a flashcard. The next rule I want us to look at is, the power rule. And this is a rule that we've actually kind of discovered in class. If you remember in the first week of school when we were finding slopes of curves using the slope formula and points really close together, we started to notice a pattern. When we had y equals x squared, we found that the slope was equal to 2x. And then we also explored y equals x cubed, and we found that the slope was equal to 3x squared. And with these two basic examples, you can kind of see the power rule. And this is what it is. The derivative of a power function, x to the n, is going to be equal to n times x to the n minus 1 power. Our exponent n is going to come to the front and become a coefficient on x, and then we're going to reduce the exponent by 1. And that's our power rule, which is also going to go on a flashcard. Let's look at a few examples of the application of this rule. Let's say that I have y is equal to x to the 9th. Then my derivative would be 9, my exponent comes to the front, it becomes a coefficient on x, and then I reduce the exponent by 1. 9 minus 1 is 8. And so my derivative is 9x to the 8th. Now let's consider this function. Let's say that we have f of x is equal to x. Now in this case, it's maybe not readily apparent that we can apply the power rule, but if I just have an x with no exponent, then remember we can assume that there's an exponent of 1. And so I can apply my power rule. This time I'm using the f prime notation for derivative. And if I apply the power rule, my exponent of 1 is going to come to the front and become a coefficient on x, and then I'm going to reduce the exponent by 1. 1 minus 1 is 0. So now I have 1x to the 0, but x to the 0, anything to the 0, is really just 1. And so this would be equal to 1. Now if you notice, this function that I started with in this example is just a linear function. And remember, whenever we're finding a derivative, what we're really doing is finding a slope. And you've known for a long time that the slope of a linear function is really just the coefficient in front of x, which in this case is 1. And so when I find the derivative, I get the slope of x, which is 1. One final example for the power rule. Let's say that we wanted to find the derivative of 2 to the 8th. Now this kind of looks like a power function because I've got a base and an exponent, but if you notice, both of those are numbers. 2 to the 8th is actually just a constant. And so since it is a constant, the derivative is going to be 0 because the derivative of any constant is 0. So just because there's an exponent doesn't mean we're necessarily using the power rule. It only applies when the base is an x and the exponent is a number. Now the power rule can show up in some slightly more complicated examples. Sometimes we have power functions that have constant multiples. For example, y is equal to 5x cubed. And in this case, if we're multiplying 5 times the function x cubed, then when we find the derivative of x cubed, we can just multiply 5 times the derivative. Let me show you what I mean. If I take the derivative of this function, it's just going to be 5 times the derivative of x cubed. And that derivative would be 3 times x squared. And then we could simplify that to being 15x squared. So really what happens in this scenario is that the exponent gets multiplied by the coefficient and then is reduced by 1 to get 15x squared. Let's look at another example like that. Let's say that f of x is equal to 7/8 x to the 10th. So in this case, 7/8 is really just a constant being multiplied by x to the 10th. And so when I take my derivative, I'm going to multiply 10 times 7/8, which would give me 70/8 times x, and then 10 minus 1 would be 9. And then my 70 over 8 can be reduced to 35 over 4, x to the 9th. Now another thing we often see with power functions are sums. Whenever we have a polynomial, it really is just a sum of power functions. Let's look at this example. Y is equal to 2x cubed plus 9x squared minus 4x plus 1. So here I've got a function, we've got 4 separate terms, and this power rule that we have, we can apply this rule to each term separately. And let me show you what I mean by that. To take the derivative of this function, I'm really going to take the derivative of each term separately. Now this step that I'm writing out here, you certainly don't have to write this step out every time. I just want you to see that what we're really doing is applying our derivative rule to each term individually. So to find this derivative, we take the derivative of 2x cubed, which would be 6x squared, plus the derivative of 9x squared, which is 18x, plus the derivative of negative 4x, which would just be negative 4, and actually I could have just put minus 4 instead of plus negative 4, and the derivative of 1, which is 0. You don't have to put plus 0 at the end. I'm just being clear that we did take a derivative of that constant term. The last thing I want us to consider are higher order derivatives. Now all the derivatives we've taken so far have been what we would call first derivatives. But sometimes we're asked to find second derivatives, third, even fourth or fifth derivatives. And all that means is that we're just going to keep applying the derivative rules over and over until we get to the derivative that we want. Let's look at an example. Let's say that f of x is equal to 3x cubed minus 5x squared plus 2. So my first derivative, f prime of x, I'm going to find the derivative of each term separately. So I'm going to start with the 3x cubed. That derivative would be 9x squared minus the derivative of 5x squared, which would be 10x, plus the derivative of 2, which is just 0. So this would be my first derivative. But now I can take another derivative. We would call this the second derivative, f double prime of x. And that would be equal to 18x. The derivative of 9x squared is 18x minus the derivative of 10x, which is 10. And I could take another derivative. The third derivative, f prime prime prime, or triple prime, would be equal to the derivative of 18x, which is 18, minus the derivative of 10, which is just 0. And so this is the third derivative of this function that we started with. Let's look at one more example just to see how the other notation looks when we're taking higher order derivatives. Let's say that we have y equal to x to the fifth. Now our first derivative we call dy dx, and this would be 5x to the fourth. We're going to denote the second derivative by putting little 2's on the d dx part of the notation. So the second derivative of y is equal to 20x to the third. And we could take another derivative. The third derivative of y is equal to 60x squared.